Good morning and welcome to the plenary session for the 2023 National Radio Science Meeting. I'm John Chisholm, I'm the chair of Commission D, and it's truly an honor to introduce our speaker for today, Dr. John Mather, who's joining us remotely from the AAS meeting. John, I see that you are on, and you're welcome to turn on your camera if you'd like. You are on the screen. First, I'd like to say a thanks to Dr. Nagara-san, who arranged this opportunity to have Dr. Mather speak to us. Dr. John Mather is the senior project scientist for the James Webb Space Telescope. And he's going to be sharing with us today some of the latest treasures from the James Webb Space Telescope. I'm sure you all know that James Webb is a mission to extend the discoveries of Hubble to look farther out into space and farther back into time. Hubble could image out to 2.5 microns. Webb can image out to beyond 28 microns. But since we're at a national radio science meeting, I prefer to think of James Webb as a 10 to 500 terahertz space telescope. So I hope you're okay with that, Dr. Mather. Dr. Mather is a senior astrophysicist in the Observational Cosmology Laboratory at NASA Goddard and the senior project scientist for James Webb. I imagine we've all seen Dr. Mather interviewed many times over the last few years as the world has watched Webb progress from final testing through the terrors of launch and finally commissioning. And in all this time, I've watched many videos of Dr. Mather on NASA television and the like, and I've been struck by how calm and relaxed he's seemed, which is pretty important when you're leading a team as large and spanning as many decades as he has. In fact, he even agreed to give this plenary before the mirrors were aligned and the instruments cooled. Thankfully, because of all the hard work of him and his team, James Webb exceeds all the performance specifications of the system. Dr. Mather is no stranger to high-profile space missions. In 1974, after defending his PhD at UC Berkeley, he led the proposal effort for the Cosmic Background Explorer, the COBE mission. COBE was able to confirm the black body spectrum of the cosmic microwave background, and ultimately that earned him, along with George Smoot, the Nobel Prize in 2006. Meanwhile, as senior project scientist for James Webb Space Telescope, Dr. Mather and his team have worked tirelessly since 1995 to bring us to where we are today. And on Christmas Day, 2021, I'm sure many of us were watching, as we all received a truly extraordinary gift with the launch of the James Webb Space Telescope. Please join me in welcoming Dr. John Mather to give our plenary address.
Well, thank you very much for the introduction. Let me see if I can master this technology. So I'm not sure I've done everything I need to do. Do you hear me? Can you see me?
Yes, we can see and hear you, but I just wanted to double check. Did you click share system sound when you shared screen? Because you have that, video in there.
I didn't see the place to do it, but to tell the truth, I'm not going to play the video, the sound from that anyway. So,
all right, then we're good.
Then we're good. Okay, returning to the slideshow, this is a summary of what we've done and what we hope to do. So there's the great telescope in space in a way that you will never see it, of course, because it is in the dark. It's a great golden hexagon, 6.5 meters across, made of 18 smaller hexagons of beryllium, all coated with gold, just enough to make it good reflector. And it is an astonishing machine. As you know, it is protected by a 5-layer sunshade to keep it cold, runs at about 45 Kelvin, so that it can pick up infrared. It has taken about 20,000 people to build it. And I can't quite imagine how to describe 20,000 people to you, but it's more than a village. It's a pretty big town. Anyways, a pretty astonishing international project with contributions from Canada and Europe. which are most essential to the mission. So I'm the senior project scientist. I'm at NASA Goddard Space Flight Center, which has been leading the mission all this time. So our job was to coordinate the effort of all these other people. You described me as leading the mission, but in truth, I am a project scientist, which means I am not a manager, and I am in awe of what the managers do. I will show you some of them and tell you a little bit about what they do, but gosh, I cannot do what they do. So here are the questions that have been motivated me since I was little. Where did we come from? Everybody knows this is an interesting question. It is remarkable that we can even make any progress on that. Are there neighbors? Where are they? And this is a biology question. Is life a miracle, or is it a thermodynamic imperative that will always occur given a chance? And if so, how long does it take? Of course, everybody also wants to know, are those things we read about in science fiction stories ever going to be possible? And I think the answer is probably not, but you never know. So stepping back in history to 1946, which is an important year for me. That's the year that Lyman Spitzer wrote a report to the Rand Corporation after the war was done and said we should build space telescopes. And he imagined that we could build them very well, that not only would they be good looking down, but they would be good for looking up. He got as far as thinking about hollowing out an asteroid and polishing a nice mirror into the surface so that would be big enough to look at exoplanets around other stars. So he was already thinking about that in 1946. Here is Sir Fred Hoyle, a cosmologist who gave the Big Bang its name and confused everybody with that name because it makes you think of a firecracker, which it definitely is not. And I don't really have time to explain much of that, but the infinite universe expanding into itself is exactly the opposite of a firecracker at a place and a time. And then in 1946, I was found under a cabbage leaf, and I've been trying to figure out what that meant ever since. So stepping back a little in history to how was it possible that we at NASA got to do what we do. In 1957, the Sputnik went up. This country was absolutely petrified because we knew the Soviet Union had nuclear weapons of immense power. They had bombers that could reach us. They had ICBMs that could reach us. And this was a proof that they could do anything they wanted to attack us. So what are we supposed to do? Well, NASA is created. Immense amounts of funds are expended by the United States to make sure that people like us would defend the nation against the Soviet Union. So Jack Kennedy said in 1962 that we're going to do all of these things, not because they are easy, but because they are hard. He also promised that we would do all the other things that were on the agenda, and that this would demonstrate that we could do great things. So it's true, we did. We demonstrated we could do great things, and now the ante is rather high. For those people that might think astronomy is a pure science, it's interesting to read about the history of the connection between astronomy and the military. There's a book called Accessory to War by Neil deGrasse Tyson and Avis Lang, and they show us many examples through time of how, beginning with Archimedes, scientists and engineers sold their products to the military as well as working on science and astronomy. So there he is, Mr. Kennedy, but I'm not going to play the whole video for you, just to remember. So here is how I got started into this scientific territory I am in now. I was a graduate student in Berkeley, finished up my doctorate in 1974 with a failed attempt to measure the cosmic microwave background radiation with a balloon payload, which is a good start on learning how to do things for NASA because it's basically a satellite on a string. So people had a lot more hair in those days. Mike Werner, who some of you may know, was the postdoc when I was a graduate student. And so he became the project scientist for the Spitzer Space Telescope, which is a pioneer demonstrating many of the technologies that we needed for the Webb, as well as pointing the scientific direction that we needed to go. So given that my thesis project failed, I was very fortunate to get a postdoc in New York City with Pat Thaddeus, a radio astronomer who was also very familiar with the cosmic microwave background radiation. So I got a postdoc there in '74, and within a few months after I got there, NASA called for satellite mission proposals. It's just 5 years after the moon landing. So what are we going to do to follow up that? So NASA expected a handful of proposals. They got over about 150 of them, including one from us. We said, okay, well, that balloon mission failed to function correctly the first time. It had worked by the second time. And so we sent it in. And this is what life was like in 1974 for me. Bicycling to work or taking the subway occasionally. And we sent in a proposal. I thought that'll never be chosen. But eventually NASA said, yeah, that's a good idea. They gave us good engineers to work with. And I got hired into NASA Goddard in Greenbelt, Maryland. And so that was the beginning of a fascinating career. So this is what we flew. The Cosmic Background Explorer satellite was launched in 1989, November 18th. And so it's now pretty old. It was followed up by the WMAP, Wilkinson Microwave Anisotropy Probe, and the Planck mission from Europe. And so the two major discoveries there that people know about, number one, we know that the spectrum of the Big Bang radiation is a black body spectrum, as it should be if the radiation originates in a thermal equilibrium process. And we also measured the hot and cold spots, which Stephen Hawking called the most important scientific discovery of this century, if not of all time. And now we can say, well, that is important because we wouldn't be here without those hot and cold spots. Those are the seeds of the cosmic structure. The gravitation acting on those dense regions was able to stop the expansion locally and turn the material back around, have it collapse into galaxies and stars. So we are here because of those spots. So there's plenty of other importance, but that's the biggest one. So we know we are here because of those spots. So and we got the Nobel Prize for this. It was actually the second Nobel Prize for this cosmic background radiation. The first prize was for the discovery by Penzias and Wilson, and back in '65. So, okay, initial conditions of the universe now understood as the universe was when it was 400,000 years old. So now tell us what happens next. Are you good at that? Well, we need a computer, and we have been puzzling over it because the computer people can never tell us the answer well enough. There are too many unknowns. So we have to go measure. So, but at any rate, the results of the COBE satellite did confirm that we were confused before. So I love this cartoon. Everything we know about the structure of the universe is wrong. So back in '89, even before the COBE satellite was launched and the Hubble telescope was launched, Garth Illingworth at UC was then at the Space Telescope Science Institute in Baltimore. They set up a conference to think about what are we going to build after the Hubble. And they got it right. They wrote that they needed a bigger telescope and they needed one that was cold enough to see the infrared sky that we couldn't be able to see with a warm telescope that glows. So that's why, as was introduced, we need a terahertz telescope and not a visible ultraviolet telescope to make the next step. So they even got about the right budget, can you imagine, for the project that we eventually built. Here's the Great Hubble telescope. Went up in April of '90, so it's almost 32 years old. And of course, as you know, it was not in focus when we launched it. It had to be repaired. And it was repaired in '93 by astronauts who took up corrective optics and new instrumentation. And it's been working beautifully ever since. The last servicing mission was quite a long time ago now, and it's still working beautifully. We are hoping to get its life extended even a little farther because we can't just leave it there. We have to either aim it at the Pacific Ocean or push it up higher so that it doesn't hit anybody. And so in the meantime, we'd like it to work as well as it can for a lot longer. So it does look like it's working well enough to be worth this effort. And NASA is discussing a reboost with the SpaceX company, possibly with their Starship. So it does things different from what the Webb telescope can do, so that's good. So here is how the observatory got started, the Webb telescope got started. Alan Dressler chaired a committee and wrote a little book called HST and Beyond. They called for two things. One is the new telescope that extends Hubble into the infrared, and one was develop the technology for the detection of Earth-like planets around other stars. So NASA has been doing both. This detection of Earth-like planets is really hard, so we're not doing it. We haven't detected them yet, really. We know where lots of small planets are, but we don't actually yet have another copy of the solar system to look at. Anyway, we started. So Dan Golden announced to the Astronomical Society that we would build this telescope only bigger. And that was a standing ovation for him. One of the few times that a non-astronomer would get a standing ovation from the Astronomical Society. So here's what it took to build the observatory. Here is the Goddard Space Flight Center team, about 200 people, which, as we now know, is about 1% of the total number of people that it took to build the observatory. What you see behind us is the steel model of the telescope that was built by Northrop Grumman to explain to people how big and powerful it would be. And you see here the 5 layers of sunshade, that's as big as a tennis court, that are used to protect the telescope from the heat of the sun, the Earth, and the moon. We put the telescope at Lagrange point 2, or orbiting around it rather, to protect it from those, and also to keep it from going too far away from Earth, where it's too hard to talk to it. Anyway, I'm in this picture somewhere, which is a reminder that everything this big is a team project. Nobody can possibly build something this big alone, and it's a magnificent result of project management skill. So here are the people that I want to especially call out for their efforts on our behalf. Bernie Siri was the project manager, study manager, to get us through the selection of the prime contractor, which was TRW, then purchased by Northrop Grumman. Phil Sablehouse took us from there until we got to where we needed more money than we had asked for and more time. And so at that point, he was succeeded by Bill Oakes, who brought us through to the launch and commissioning. And Scott Willoughby there at Northrop Grumman was the project manager there to lead that team. So pretty astonishing results that these people made possible. There's a project management skill that is way beyond anything I can imagine. And I'm so glad that they were able to do this when I could not possibly. I want to also call out Senator Mikulski. Barbara Mikulski of Maryland was in the Senate for, I think, 6 terms. By the time she completed her service there, she had managed to save the Hubble and get it repaired by finding the necessary support within the legislative branch. She managed to tell us that we needed to have a better plan for the Webb telescope, that it was embarrassing for her and everyone to keep asking every year for just a little bit more money. Why don't we make a plan that we can actually carry out? So we did. We got review committees from Jet Propulsion Lab to take a non-advocate view and to tell us if we were doing it okay. And was the new plan good enough? So the answer was yes, it was, and she managed to get the necessary support to have it happen. Among other things, she was a person who wanted to be a scientist before she became a politician. So she found that chemistry was a little hard, but then she took on a much harder job of being a politician. So thank you to Barbara Mikulski. We have named the archive of space telescope data in Baltimore after her. So we had to develop 10 new technologies in the time from 96 to 2002. We needed 2 flavors of new detectors, actually based on what we already could do, but they had to be better. We needed a little cryogenic computer chip that could run at 40 Kelvin to run those detectors and amplify the signals and send out bits. We needed better infrared, mid-infrared detectors, what you would call high terahertz detectors. Needed a cooler to keep the mid-infrared instrument running. It needs to run at 7 Kelvin to make those detectors work well. And one of the other things to obviously point out is needed to learn how to focus the telescope to measure whether it's in shape or not. because all those 18 hexagons are independent. And so then they are launched, they are not aligned with one another. The way we do this is to take advantage of the analytic function of which represents the electric field in 3 dimensions, which means that amplitude and phase are correlated. So that means if you can take enough pictures of out of focus images and run them through a computer program on the ground, you can determine how to adjust the little actuators behind the mirrors and put them in the right place. So that works because, of course, we rehearsed it many times. So here is the telescope design. It's called a 3-mirror anastigmat, which is a very fast primary mirror, a hyperbolic secondary mirror, and a third mirror, which is ellipsoidal. And it achieves a very wide field of view with excellent image quality. We required for the engineering specifications 150 nanometers RMS wavefront error, which is diffraction limited at 2 microns. The upshot was it's diffraction limited at 1.1 microns, which we are very proud of. A special technology we had to invent was the fabrication of mirrors that would be the right shape at low temperature. So they're made of beryllium, about 2 millimeters thick. And so the way we do it is we build them at room temperature, we measure them at room temperature, we measure them at a low temperature, the ambient temperature they will have. We warm them up, confirm that they weren't permanently damaged by the cooling, and they weren't. Then we polish off the bumps that were left that we needed to remove. So the next time it's cooled down, it will be the right shape. So we did that and it works very well. The actual method of polishing the beryllium to the right shape is a trade secret, and I do not know how it's done, but they know. The company that did it knows. Tinsley Laboratories. So here is the instrument collection that we flew. Has 4 instruments on board, near-infrared cameras and spectrometers, a mid-infrared instrument with both, and a fine guidance sensor with another spectrometer provided by Canada. If you are an astronomer right now, you are about to write and submit a proposal to use these instruments. Proposals are due very soon. So anyway, there's the list of capabilities. It is extremely general purpose. We knew when we started that although we had ideas about the most scientifically important things to do, that time would pass. And now we know that much more time can pass. The observatory's predicted life is at least 20 years, as limited by the fuel consumption, which we need to maintain the orbit and to maintain the pointing control of the system. So there it is, what we have flown and what you can use. These are the people, some of whom you may know, astronomers who were in charge of the 4 instruments. John Hutchings in Canada was the project scientist for their work, succeeded by René Doyon. Peter Jacobsen in Europe was their project scientist and succeeded by Pierre Ferrouille. In our country, here in Marcia Ricci in Arizona was the principal investigator for the camera near infrared. George Ricci, there also in Arizona, worked in partnership with Gillian Wright of UK Advanced Technology Centre in Edinburgh to make sure the mid-infrared instrument would come together. Gillian was the person who coordinated the efforts of, I think, 14 European institutions to contribute their pieces to this great instrument. I thought that would never work, but she made it work. So here is the science working group. These people were chosen in 2002. This is actually the 3rd science working group following the 2 that existed before the selection, the competitive selection. So these are all brilliant people who've put their shoulders into the work, put their hearts and minds and time into the work, and made it happen. So they worked with us to make the project together. This is the project science team at Goddard Space Flight Center. I'm the senior project scientist at Goddard, and John Gardner is deputy senior project scientist. He was the person who actually made the whole system run well. And all of these people worked with our engineering colleagues to make sure that everything that we had asked for was being done the way that we hoped it would be. And once in a while, contributing some creative thoughts to making it a little better. So we have recently submitted to the publications of the Astronomical Society of the Pacific 9 papers describing the instruments, the operations, the telescope, and everything about the observatory. Pretty soon it'll be officially published. These papers are now appearing on our archive.org preprint servers for astronomers. So it's done, and it works beautifully. I want to show you some of the charts that Jane Rigby made for our first science conference in December. Here is a selfie of the telescope itself. We have the ability to take the picture because we needed lenses to help with the wavefront sensing, to focus the telescope. So her summary chart says everything is better than expected across the board, including sharp imaging, better pointing, better guiding, better efficiency. And not only that, it's clean. Keeping the telescope clean so that it wouldn't have stray light is quite an interesting challenge because the mirrors are dusty. They can't avoid being dusty, but starlight and other light scattering off the dust on the mirrors will contribute something called stray light, and it'll make the observatory, it'll take longer to get the picture we need if there's a lot of stray light. So that was done. Some example of performance. Here's great, beautiful Jupiter. And you can see lots of interesting features of Jupiter. You can see that it's got a sort of ring around the picture. There's a glowing layer in the atmosphere. There is an orbiting a dust particle ring, which we knew existed, but we see it very simply in the infrared. There's an aurora about the north and south poles. You can see several of the little satellites. So anyway, this is also a tour de force of image processing, because while we're taking the picture, the parts are moving. Jupiter is rotating, the satellites are moving. So if you want to get this picture, you have to work quite hard at raw data. Here is how we see the telescope's wavefront error. I mentioned that we have this ability to calculate, and this picture shows you that we got one interesting micrometeoroid impact. We get actually about one a month, which have almost negligible impact, but this particular one was a bit of a surprise because it hit something and seemed to have bent the mirror enough to make almost a micron error in wavefront error. So we are not quite sure how it happened. Either it hit a vulnerable spot or it was very, very energetic. So we don't know how to estimate our statistics for this, but so far we've only had one of them in a year. So at that rate, we'll be fine. So we are going to try to minimize the rate of those events by keeping the back of the telescope towards the wind, looking away from the flood of micrometeoroids. Hope to reduce the rate of events and the severity. So we had a chart like this to show the 4 scientific themes that we're going to approach with the Webb telescope observations. I've got little check marks to say all of them have been accomplished already. Look at the first light, that is to say the first stars and black holes to grow from the Big Bang. How do the galaxies grow? We're using gravitational lenses to find that out. How do stars get born? We can see inside the dust clouds. And finally, what about those planets? We can see them. Some of them we see directly. Most of them we study are seen by the transit technique, which I'll show you. Here is the picture we first released from the White House. President Biden showed this picture to the world. Our operations scientist, Jane Rigby, showed it and explained it. So what do we see in the picture? We see a wonderful star there in the middle with the 6 spikes sticking out, bright ones. Those are due to the hexagonal mirrors with their diffraction. We see some enormous, very bright galaxies in the center. The diffuse glows there are the galaxies themselves. We see some very interesting curves, which is our distorted images of distant galaxies. You know they're distant because they're red. And we know that there's distorted images because they don't look like galaxies anymore. These are distorted because of the gravitational forces of those galaxies that you see in the middle operating on the light coming from more distant places. By the way, the light from the Big Bang is deflected by about 2.5 arc minutes on its way to our observatory. So it's a much bigger effect than you might intuitively expect. 2.5 arc minutes is, what is that? Almost 10% of the size of the moon. So the gravitational fields out there are really doing something to the images that we get. It's a very strong effect. And we'll show you some of what we got using those gravitational lenses. Here's one thing that we could tell also. We try to subtract out all the light from the galaxies that are in that picture and say, what about the glowing region around the galaxies? So this is important because we'd like to know what is the mass distribution of material in that cluster of galaxies in the foreground, so we can see the glowing light around them. So a hint about where is the dark matter also. This is our approach to finding the most distant galaxies. We take a picture with the camera. We identify objects that seem to have the reddest colors. We say, well, that's a worthy target for the spectrometer. So then we set up the spectrometer to get a spectrum of each of those little fuzzy dots. And we look for a thing called the Lyman break. The intergalactic hydrogen, neutral hydrogen, absorbs all wavelengths shorter than 912 angstroms, which is the wavelength that it takes to ionize a neutral hydrogen atom. So it's just opaque at short wavelengths. We look for that marker in the spectrum, and we see it here, but we see that wavelength redshifted by the expansion of the universe, and so we can detect the shift, the jump in the spectrum, as a marker of the redshift and hence of the distance. So we are seeing with this technique some galaxies that are formed within a few 100 million years of the beginning of the expansion, the Big Bang itself. So that's our method for finding them. And of course, we keep on working on this because it's one of our top targets. The short version of the answer is there are too many of those early galaxies. They are too big, too bright, too hot, too mature, and too soon. So this is a bit of a surprise for us that have been working on this subject for a long time. And I don't know what the explanation is going to be. At any rate, it's a very hot topic, and it's one of our major results already. Big surprise about the early universe. We are able to study the motions of gas orbiting around quasars. Quasars, as you know, are black holes. And when material falls in and to the black hole, it gets compressed on the way in and it's heated to enormous temperatures, capable of emitting even X-rays. Here it is, we see in the colder material farther away from the quasar and measuring its velocity distribution. So we can use our spectrometer to map the presence of, say, doubly ionized oxygen and how it's moving in the neighborhood of the quasar. So this we use to tell us how does material get turned into new stars and how is it going to fall into the quasar. This is one of the more startling things we got. This is a gravitational lensed picture of a very distant galaxy at a redshift of 1.37, which means we're looking back about 9 billion years towards the earliest moments. This is a galaxy which shows the presence of globular clusters. Now here in the Milky Way where we live, there are a few globular clusters. This image of an early galaxy has them everywhere. And this was called a sparkler because there are so many. We can study them, enumerate them, get their spectra, and think about what they mean, because it does look like globular clusters are among the first populations to grow from the Big Bang. Our question is, do they form first and then assemble themselves into galaxies, or does the opposite happen? Here is an example of an extremely magnified set of objects in one of those galaxies. Excuse me. On this right-hand side, you're seeing something called the lensing critical curve. This is a curve showing that there's unlimited magnification at for objects that are on this particular curve in the most distant galaxy. So what we're seeing here is in this magnified image, a series of double images. There's a C on the right-hand side, you see something called the lensed star. Then on both the right and the left, there are numbered images, 1.1a and 1.1b, which are two images of the same object. The remarkable thing about the lensed star is that it seems to be exactly on the critical magnification curve, so that we see an individual star at this immense distance. Sometimes there are even three images. So look here in the lower left corner of this image, there's a 1.1c way down here. So not unusual to get all these multiple images of the same object. So we seem to find an individual star every time we do this, which is something we've talked about in the earliest days, and we thought, well, that'll never happen. The probability is too low. But actually, the result is it always happens. There's always an individual star right on that critical curve, and here's a spectrum of such a star as observed by the Webb. An ordinary star, a 10,000 degree B star. We didn't expect that we would find supernovae easily, but right away we saw one. This is a discovery picture. You compare the picture taken by the Webb with the picture taken by Hubble, take a difference, and you see a little dot as marked by the arrows here, and that's a supernova. This is a laboratory for star formation. This is an image of a cartwheel galaxy, as we call it. The little red galaxy in the upper left went flying right through the exact center of the big galaxy and set off a splash. You can see the gas that was expelled from the center in the splash, and it's in the process of forming new generations of stars in that little ring. So how are galaxies grown? Well, this is one of the processes. Another wonderful surprise we got is that galaxy that looked like a perfectly ordinary spiral galaxy is seen to have holes in it in the mid-infrared. So what are we looking at here? We are seeing gaseous material and dust with the mid-infrared instrument. And for example, in this little hole in the lower right-hand corner, this is an area where a burst of star formation occurred. Bright new stars, very, very hot, send out immense amounts of energy, kinetic energy and light energy, and they start to burn a hole in the neighborhood. So the result is an outgoing wave of gaseous material, which prompts the growth of new stars in the shell around the hole. And now we can see it directly with our mid-infrared capability. By the way, this is also pointing out that there's a possibility for amateur image processors to work on our data. Judy Schmidt lives in Modesto, California, and she does this from home. So thank you, Judy. This picture is also showing us the blue core of this particular galaxy. It's blue because we're seeing the stars right there in the middle. And for whatever reason, there's not a lot of dust obscuring the view down there. This is the pillars of creation, which we have been talking about for decades as observed with the Hubble telescope. So anyway, it is seen very differently with the mid-infrared capabilities that we have on the Webb. You see new generations of stars being born. You can very clearly see the effect of the high velocity wind blowing around this cloud. And why is there a high velocity wind? It's because new stars from this cloud were born in the upper right corner, and they, as I said before, are sending out immense amounts of energy, blowing material away. So as an example, there's quite a few objects like this little one here where there's a star being born, and you can see what the wind blowing by is doing to the material around it. So this is one of the ways we learn about how stars are born. We see into these clouds. And why can you see into a cloud with a mid-infrared? Well, number one, dust grains are scatterers, and they're pretty good scatterers for wavelengths comparable in size to the wavelength in question. But if the wavelength is much longer, they're not very good scatterers. So that means that the long wavelength infrared allows us to see inside clouds that were otherwise opaque at the shorter wavelengths. So we're now seeing through the dust into the insides. Here's a new star being born. This is seen directly with a mid-infrared instrument, as well as the near IR. And we have it oriented so you can see that across the middle of the object is a dark line. That means that we are seeing that it's dark because there's a disk of material orbiting around the new star in the center. So I have it magnified here so you can see that better. Now we expect that right down there in the very middle of the picture is a new star, which you cannot see, although it's lighting up the neighborhood. We are seeing it edge on in the set of, and there's our dust grains orbiting around that star, presumably in the process of forming new planets. So I'm sure that we will be looking as well as we can into this disk to see the new planets being born. We have a few places where we already know there are planets. This is another edge on disk where there's a new star in the middle. And it's bright enough that it already had a name because you can see it with a small telescope or binoculars. Anyway, this has 2 planets, and now we can see that it has a disk of orbiting material, which we will now pursue to see, do we know how this works? How are solar systems born? We said we would observe the formation of new planets. So here is our story that we told before we launched the telescope. We said we would observe 62 planets in the first year by this transit technique. We wait and point the telescope at the star when a planet is going to go in front of it. Of course, we only know when to do this because somebody has already discovered these transits using other equipment, mostly with the TESS observatory, but some even can be detected directly from the ground. So we have a catalog to look at. The most interesting ones might be the small ones, which are potentially habitable in the sense of being the right temperature and the right size to have life like ours. The obvious big question is, do they have an atmosphere? And that would be a sign that they're more like Earth than just a rocky planet. Then we look at bigger ones that are similar enough to be interesting, but anyway, I'll show you that we can do this technique because we've observed the atmospheric contents of this star, this planet. It's a big hot one. It's a hot gas giant, which means it's comparable in size to Jupiter, but it's much closer to its star, so it's warm and it's pretty easy to study. So we observed it with 3 different instruments in 4 different ways to see what do we do, and we can see so what we see here is that the amount of the planet, the amount of the star that's obscured by the planet depends on wavelength. And that's because the molecules in the atmosphere of that planet absorb at some wavelengths more than at others. So we have sodium and potassium and carbon monoxide and carbon dioxide and water and sulfur dioxide all in the atmosphere of this one planet. So we demonstrate with this method that we can do the observations that we need. We have to predict and guess what would an Earth-like planet be like. And the calculation we make currently is, this is a really hard observation. So we're going to try, and we are trying, to look at small Earth-like planets in front of the most promising small stars. You probably all know that small stars like Proxima Centauri are very hazardous, though also they put out lots and lots of puffs of ionized plasma that could be enough to rip the atmosphere right off of a planet. So we don't know whether this is enough or not. So the answer is you have to go look. We have, of course, observed some planets directly when they're very big and very bright, and then we can see them directly. So not all planets are are seen by reflected light only. This planet is hot enough, bright enough, that it's still shining from its own internal heat. So how does a planet get hot when it's not being heated by its own star? When it's being formed, it starts off large and starts to shrink. So gravitational potential energy is converted into heat, and that makes the hot planet big enough to see, bright enough to see. Here is a thing called the Southern Ring Nebula. A ring nebula is a star in the process of disintegrating. So the star sends off puffs of material from time to time. Usually they're spherical, but this one is certainly not. So the question in our astronomers' minds is, well, why not? What is going on here? So the right-hand side, you can see the mid-infrared picture. You see there are two stars in the middle, not just one. And we'll magnify it a little bit here so you can see them better. The redder star in the right-hand side is the source of the dust. And we are beginning to see into that, through that dust, with the mid-infrared capabilities. As I mentioned, the dust is less opaque at longer wavelengths. So we still haven't really understood it, but there is a story about how this could happen involving 5 different stars. And that would be why, if this story is true, that would explain the strange shape of this planetary nebula. So what else have we looked at? Well, we can look at all of the planets in the solar system from Mars on outwards. We can't look any closer to the sun than about 85 degrees. Otherwise, we'll get sun on the telescope. So that tells us what we're able to see. So I showed you that Jupiter has rings around it, so does Neptune. Everyone knows Saturn has rings around it, but even Uranus has rings around it. So it seems to be a very popular, common event. And here you can see Neptune has really bright clouds in its system. And they sort of shine out because they're in our wavelength range, they shine out because they're hot or hotter than the other areas. We got pictures of Titan. Titan is big enough to have a thick atmosphere. Titan is a satellite of Saturn, and you can see we are measuring its clouds with the JWST. We can even do a chemical analysis of this system with hundreds and hundreds of spectrum lines coming back to us to tell us about the detailed chemistry of that atmosphere. In about 11 years, we are planning to land a helicopter on that surface. And the engineering of that is another engineering marvel to be discussed later, perhaps. We have attacked an asteroid, as you know. The DART, it was the deflecting an asteroid with double asteroid redirection. So we put an impactor onto the asteroid and measured the debris coming out, both with the Hubble and the Webb, to be able to track this object, which moves much faster than the specified capabilities of the guide system for the JWST, was a major accomplishment. By the way, you may know that the kick that the asteroid got was much larger than the kick from the momentum of the impactor, because a lot of debris comes flying out and has the kind of effect of an additional rocket thrust because of that. Chemical energy is converted into thermal energy, which expels material and adds to the thrust. Here is one of our startling pictures. This is shows dust rings put out by a binary star. So there's a category of star called the Wolf-Rayet star. It's a very old, bright star, and it's in the instability region where it is got an atmosphere that can be tugged on by the it's a binary companion. So once per orbit, it sends out a pulse of dust in all directions. And here's a model for how this happens. So this is seen in the mid-infrared. We would never have known about it without the Webb telescope capabilities. So what are we doing next? NASA has a partnership with European Space Agency to contribute to the Euclid mission, which is supposed to go up this year on a SpaceX launch. We have to do that because Russia attacked Ukraine and we're not using Russian rockets anymore. Anyway, we have negotiated now that SpaceX will carry this into space pretty soon. This instrument is to look for dark matter and dark energy and do a wide sky survey. We are about to start up observing with the Vera Rubin Observatory. Vera Rubin was one of the scientists at Carnegie Department of Terrestrial Magnetism, and they call it, in Washington. She was one of the people who pioneered the study of dark matter, which you can detect by its gravitational effect on the rotation of galaxies. So we've named this observatory for her. Actually, it was named through a congressional resolution, I think. At any rate, this is a huge telescope on the ground, 8.4 meter mirror, a huge field of view. Will observe the entire sky every 3 nights. And it is capable of sending out alerts every time something changes from night to night. They are expecting 10 million alerts every night about something that changed. So get more graduate students. Need some way to cope with this flood of interesting, but possibly not unique alerts every night. We NASA are about to launch the Nancy Grace Roman Space Telescope. Nancy was the chief astronomer at NASA headquarters for a very long time, a wonderful person to work with. Anyway, that we've named the telescope for her. This is a little bigger, about twice as big as the Euclid mission, and we think it'll be more powerful for the dark energy and the dark matter surveys. We'll also be looking for things with a coronograph. A coronograph is a device to block the light of a star or a quasar to see what's around it. And so we'll be able to study exoplanets better than ever before with direct imaging. So NASA has now received a desire from the National Academy of Sciences to produce a thing called the Habitable Worlds Observer, which is at least as big as the Webb telescope, but designed specifically to be able to see exoplanets orbiting stars like the sun, which is one of the most difficult observational things we could imagine, because the sun is 10 billion times brighter than the Earth. So this will be a hard project, but it is the next big one that we have been asked to do. So I'm pretty close to the end of my time allocation, but I just wanted to show you a couple of other things that I have in mind to think about. You know, we have great observatories being constructed on the ground, much bigger than we can put into space now. There's a European one, the most mature, it's 39 meters across. It's 6 times as big as the Webb. So we need to learn how to use it as well as we can. We need something we don't have called adaptive optics at visible wavelengths. So it is possible, but extremely difficult. But if we can get that to go, then these giant telescopes on the ground can actually do things that we will never be able to do with space telescopes. And so it's worth opening up that observational window. It is possible to build hybrid observatories, something with a piece on the ground and a piece in space. So adaptive optics, photometric calibration, guide stars, even exoplanet detection. So we can put up a laser guide star to focus on for adaptive optics. We can buy all the parts for the space part already. So this is logically possible, and it might even be better than the other methods for some purposes. We need a way to phase up the dishes of the imaging interferometers. Navy has one that works, but we gain a factor of 1,000 in sensitivity if we had a space beacon to focus on. Excuse me. This is the wildest idea that I'm working. It's an orbiting star shade. If you could build it, it's 100 meters across, and put it in the right orbit, you could get a picture of a solar system in 1 minute with Earth, Venus, and Mars all showing up very easily. Not impossible, just really difficult. So we could extend the Event Horizon Telescope that observed the black hole by putting up another antenna in space to work with it. That would help too. So we have obtained, I should say, we astronomers have gotten 4 Nobel Prizes in the last decade, which is totally astonishing to me. It means that we are working on things of fundamental physical importance, from the acceleration of the universe, the dark energy, the detection of gravitational waves, detection of exoplanets, cosmology, and finally black holes. So more to come. I don't know what it's going to be, but we're encouraging our astronomer community to be submitting proposals. Proposals for JWST are due on the 27th. So we still have a few days left to finish those up. And now, however, we have recognized that it's possible for the ChatGPT to write a pretty decent proposal. So this is astonishing. So a lot of new technology to think about. And let me take, if we still have a minute or two for questions, I hope we can answer some of your questions. So thank you for the attention, and let's see what we can think about together.
Okay, time for a couple of questions.
Yeah.
Hello, is this mic on? It is, I think. Thank you so much for the talk. I feel just kind of honored listening to it, in fact. My question is, will the James Webb Telescope and its new capabilities be able to shed light on the supermassive black holes, which live at the center of galaxies? Is that something that's in the cards?
Yes, it really is. I showed you one picture where we're observing the material orbiting around one at a high redshift. So the big question astronomers have had for generations now is, which comes first, black holes or galaxies? And which one grows the other one? So we don't know that answer yet, but we hope to find out with the Webb by many different approaches. It's one of our top priorities.
Yes, thank you very much. That was really very rewarding for us to see what this James Webb Telescope is doing. I have maybe 2 related questions. You might have alluded to it. One is that, if I understood correctly, the James Webb is capable of looking after the black hole about 380,000 years past black hole. And then the speculation was that before that, it should not be so much mass or big objects. And as you said, they are seeing things that it was not expected. So what is the thinking about that? What is happening?
Yes. Well, what we've done so far is we have an image of the early expanding universe as measured with the COBE satellite and the WMAP and Planck missions. So we have the hot and cold spots across the entire sky. So that's the closest we can get to an image of the Big Bang itself. So we look back in time to those days when the universe went from opaque to transparent. So it's like looking at the surface of the sun, except the entire universe. Then we have something called the cosmic dark ages, when there were no objects that we know of to observe. So that's lasts for a few hundred million years, perhaps. And then we are looking for the first galaxies that grew from that material. And we found a few that are from the first few hundred million years. But in between the the cosmic microwave background map and those first galaxies, nothing is known at the moment. So that's
yeah, maybe the follow-up question, if I may. This notion of dark energy and dark matter, of course, is very confusing to many of us who are not radio astronomers or astrophysicists. What signatures do we look to identify if dark matter does exist or dark energy?
So the gravitational, okay, so dark matter is recognized through its gravitational effects. First evidence was that galaxies rotate much too fast. if you can't explain how they have enough gravity to hold themselves together, if you just add up the parts you can see directly with stars and gas. So the masses of galaxies are deduced to be much larger than the apparent mass. So that's one of the first. We have other similar observations of clusters of galaxies, the gravitational lensing effects. So it's all gravitational that tells us about the dark matter. The dark energy is something else again. It's a feature of the universe. The universe appears to be expanding rapidly and accelerating as it goes. So we call that the dark energy, but honestly, we know nothing about it. All we know so far is that it fits the constant of integration in general relativity that's called Einstein's lambda constant. So we don't know if it's anything except a feature of gravity or the expanding universe, and so it does not. We have no evidence about what made it happen. Physicists do not have a prediction for it that makes any difference. The original predictions are off by 120 orders of magnitude. Obviously, we don't understand it. So if you ask, what is it really? Nobody can tell you.
So we have time for one more question.
Thank you, Dr. Mather, for the talk. I was just wondering what you'd summarize and say your takeaway from being involved with JWST was, both from an engineering perspective and because you alluded to it from management. And just leading on from that, do you think JWST makes LUVOIR more likely or less likely?
Okay. Well, takeaway is when you have a sufficiently inspiring but extremely difficult project, it is possible to do it when you can explain it well to the people who would fund it. So the Congress funded this despite all of our troubles because there's really no other way to get at this. Astronomers all supported it. They were a little afraid of the price, but they have all supported it. So community support is essential. Now we have demonstrated that we can do really hard things. So I think the pathway is pretty direct to the next one. It's now being called the Habitable Worlds Observatory rather than LUVOIR, but we know what to do next. So I think we are going to be able to do it. So I'm very optimistic and I'm happy to contribute my thoughts to making it successful.
Dr. Mather, thank you so much for joining us, giving us a glimpse into our universe. Would you all join me in thanking Dr. Mather?
Thank you so much.
Yeah, I will add my thanks as well. I know Dr. Mather has a busy schedule, and we appreciate that you could join us from Seattle. So this is going to conclude. So this will conclude our session. I want to have one more round of applause for both our speakers before we depart. Okay, so next up we have for our students, there's a student mentoring lunch that will be in the Coble Auditorium. I'm sorry, a room in Coble Hall. We also ask that each of the commission chairs or their representatives join us because we want the students to be able to interact with our commissions. We'll start that up as soon as possible. There should be people outside that will direct you in that in the right area. So thank you again for a great plenary session and have a great rest of the radio science meeting.